Welcome. On this video, we're going to be discussing the natural exponential function. But before we discuss the natural exponential functions, we have to introduce a new number, and that is the Euler number. What is exactly the Euler number? Well, let's take a look at this small introduction question. It says another way to express an exponential function is by using the letter E, which that it is the Euler number. And for large numbers, the expression 1 plus 1 over x all to the x can be used to approximate the value of this number. So if we take a look at this expression, 1 plus 1 over x all to the x, the larger the values of x's that we plug into this expression, the closer we're going to get to the value of the Euler number. So let's actually calculate the value of this number. And again, it's not going to be an exact value, but we're going to get a good approximation for it. So what is this approximation? Well, let's go to decimals. So here we have our function, 1 plus 1 over x all to the x. And let's just plug in values of x's. Well, notice that we're just going to be plugging values of x, but those values are going to be increasing. So if we plug in 2, if we plug in 1, we get a 2 out. If we plug in a 2, we get a 225 out. So let's plug in 3, 4. Let's just go faster. So let's plug in a 10. Notice that you get 2.59. Let's plug in an 80. Notice that we're getting 2.70. I don't know, let's go to 100, 2.70, 150. Well, it seems like we're kind of getting closer and closer to the value of 2.70. I don't know. Let's just keep plugging numbers. Oh, notice that when we go to 200, so if we were to plug in 200 to our expression, we're going to get 2.71. So let's just, I don't know, plug in 500. Still 2.71. Let's just keep plugging in values that are higher. So 1,000 to 2.71 still. I don't know. 1, 2, 3. 2,000. We're still at 2.71. I don't know. Let's just plug in 10,000. So notice that as we're getting closer, notice that as we are increasing in value, the function itself, it seems to be getting closer and closer to the value of 2.71. Let's just plug in. Notice that even if there's a huge difference between this value and this value, and that huge difference doesn't really make too much of a difference on the outcome. So this expression itself, as x is getting larger, or as x is going towards infinity, the expression itself is getting closer and closer to the value of 2.71. And that's actually the value that we're going to be using to properly estimate the Euler number. So that is a value that we have to memorize. And the value is that the Euler number, which we're going to use a letter E on it, it's approximately 2.71. And again, that doesn't mean that the Euler number, it is exactly 2.71, because notice that there's still a bunch of decimals after this. And notice that, I don't know if it's too clear, but then after this 8, it's 0.5. And then if we plug in 2, what's that, 2 million? That's 811, and I'm pretty sure if we're plugging 3. Notice that it's still 2.7182, but notice that we're still changing. It went from 11 to 14, so it's not an exact value, but it's a good approximation. So we're going to use the value of 2.71 as the approximation of this Euler number. And this is a value that is very important to memorize. And now that we have introduced the idea of the so-called Euler number, what is exactly a natural exponential function? Well, a natural exponential function, it is an exponential function where notice that now the base is not a number. The base is the Euler number. And that's what we're going to refer to as the natural exponential function. It is an exponential function since the variable, or the unknown, it's on the exponent. But since the base is this so-called Euler number, then we refer to that as just as the natural exponential function. And since they're both exponential functions, well, when do we have an exponential growth and when do we have an exponential decay? And for that, we're going to take a look at these two functions. 2 to the 2 base e with an exponent of 20.24x, and 1 half e to the exponent of negative 0.58x. So let's graph one at a time. And let's concentrate on the function of 2 to the 2e to the 0.24x. So right now, let's try to graph the first function, which notice that if we graph it, we get this exponential function for sure. And notice that this is an exponential increasing function or an exponential growth. And based on this graph, let's just analyze it. So we try to answer this question. So where is my function increasing? Well, if we take a look into my function here, it seems that my function is increasing everywhere. Because if we zoom out, if we still zoom out, notice that as we're still moving to the right-hand side, my function, it is still going upwards. So this is a function that is increasing everywhere. So therefore, the interval where my function it is increasing, it is from negative infinity to positive infinity. It is always increasing. And again, f of x, right now, this refers to the function of 2 to the e 0.24x, and the graph is the one that we're looking at decimals right here. So it is always increasing. So if it's always increasing, where is it decreasing? Well, it is never decreasing, because if it's always increasing, then it just doesn't make sense to say that it decreased anywhere. So where is it decrease? Well, none. There is no value that will, well, there is no interval where the function will decrease in value. So what is the limit of this function as x is getting closer and closer to infinity? In other words, if we take a look at our function, the farther we're going to the right hand side, what is the direction that the y's are taking? Well, the farther that we move to the right, my function, we already established that is increasing, so therefore my y values are always going to be going to positive infinity. So therefore, the limit of this function as x is going to infinity, well, that is infinity. Because if it's always going to be increasing, then the function has a limit of positive infinity. Now, is there any asymptotes that this function has? Well, let's see. Definitely not a vertical asymptote, because it's always going to be moving to the right-hand side. Even when we move, well, I mean, it's not that clear, I guess. I over-exaggerated there. But it's always going to be increasing, and it's always going to be moving to the right. So there is no vertical asymptote. But notice that we do have a horizontal asymptote, because notice that if we keep scrolling to the right-hand side, my function doesn't seem to be passing the y value of 0. And if we zoom a little bit farther out, notice that this is still my function, and we seem to be having a horizontal asymptote at the value y equals 1. So let's write that down. Is there any asymptotes? Well, there seems to be a horizontal asymptote at the value y equals 0. So this takes care of a increasing exponential or natural exponential function. But now let's take a look at g of x, where again, g of x is a natural exponential function, but now notice that we have a negative exponent. So how is having a negative exponent going to affect the behavior of my function? Let's see. So let's erase this. And now let's graph the function with the negative exponent. Now notice that when we switch it to a negative exponent, we don't have an increasing function anymore, but now we have a decreasing function. Because notice that as I keep moving to the right-hand side, my y values are decreasing in value. And we seem to be having another horizontal asymptote at 0. So is my function increasing? No, we just established that it is never decreasing, increasing. Therefore, where is it increasing? Well, there is no interval where my function it is increasing, because we just established that my function is always going to be decreasing. So where is it decreasing? Well, it is decreasing everywhere. So therefore, we can say that it's decreasing from negative infinity to positive infinity. Now let's try to find the limit of this function. So what y value are we seem to be approaching as x is going farther to the right? So what is the limit of the function as x is going to positive infinity? Well, let's see. The farther we move to the right hand side, the closer we seem to be getting to zero. And we seem to be just having a horizontal asymptote at zero. So if we take a look at the values, we seem to be just getting stuck at zero. Which again, I guess this is just decimals, because I don't think we're actually stuck at zero, but decimals is just saying, well, you're pretty close to zero, so I'm just going to call it zero. So in this case, the limit seems to be going towards a value of zero. Is there any asymptote? Well, notice that we still have the same idea of a horizontal asymptote at the value y equals zero. And these two examples can help us illustrate the big idea for natural exponential functions. So for any natural exponential functions, we're going to have a decreasing function or an exponential decay if the exponent is negative. And we'll explain that in a second. And we're going to be an increasing or an exponential growth if the exponent is positive. So why is that? Well, notice that now under a natural exponential function, the base, it's a fixed number, 2.71. So the only thing that is changing is just a negative value. So if we have e to the x, we can think about this as if it was 2.71 to the x. And now notice that my base is greater than 1, so therefore it is an exponential growth. It will be increasing in value. So now if we have a negative exponent, this can be seen as 2.71 to the negative x, which again, if we want to represent this as a positive exponent, we got to just take the reciprocal. So that would be 2 over 2.71 all to the positive x. And notice that 1 divided by 2.71, this is always going to be less than 1. So therefore, it is an exponential decrease or an exponential decay function. So this is very important for us to understand. Under a natural exponential function, it's all about the exponent, the sign of the exponent, not like we discussed previously. Because since the base it is fixed to be about 2.71, then everything's been determined by the exponent. Positive exponent, exponential increasing. Oops, I just saw that I just put them in the wrong order. Well, it's not nice, but hopefully you get the idea. So it's an exponential increasing if the exponent is positive, exponential decreasing if the exponent is negative. And this is the summary for today's lesson. I wanted for you to just see that there is this new function, which we're going to call a natural exponential function. And a natural exponential function is that function that has an Euler number as the base. And the Euler number is to be approximately 2.71. And we're going to have a decreasing exponential or an exponential decay if my exponent is negative. And we're going to have an increasing or an exponential growth if the exponent is positive. And with this, we conclude our lesson for natural exponential functions.